Graphing trigonometric functions, gaining intuition and insight. A few weeks ago I did a graph of a triangle. This week we will continue with graphing. We will look at graphs of trigonometric functions like sine, cosine, tangent, arcsine, and others. Why graphs? What do they do? Graphs allow us to see relationships more intuitively. Intuition leads to insight, which leads to discovery, which leads to proofs. Let's look at a simple example. So exercise 1, we're going to create a table and then plot sine and cosine over 2 cycles all the way to 0 to 4 pi. So what can we say about sine and cosine based on this plot? Probably could say a lot of things. So let's just create this data. Very simple. That's 1 degree. Sine of, well, that's 0 degrees, but we're going to increment by 1 degree. All the way to 720 degrees. Then we're going to highlight the chart area, and we're going to insert a chart, and just quickly format this chart a little bit. The labels have to be next down low, and the spacing, I'm going to space at 90, and then I'm going to put some axis titles there, and then I'll move the legend off to the right. That'll make it look a little bit nicer. Alright, so here's the final product, and what can we say about sine and cosine? Well, I think it's pretty obvious. Just look at it. They are the same function. They're just shifted by pi over 2. That's easy to prove. So sine of theta is cosine of pi over 2 minus theta, but that's minus theta, that's negative theta, that's not what we wanted. We can use that cosine of minus x is equal to cosine of x to switch it around. Okay, that's good in one direction. Now we'll do a substitution. Psi is equal to theta minus pi over 2. I plug that in there and we can get a similar expression for cosine. Cosine of psi is equal to sine of pi over 2 plus psi. And we could change it to theta as well because it's a dummy variable. But yeah, that's what we wanted to show. So exercise 2. Tabulate and plot sine theta and theta over the range from 0 to 60 degrees. Okay, what can we say about sine theta and theta based on this plot? Okay, let's go back to the spreadsheet. Here we're creating exactly the same data that we did to the left. We could have just copied it over, but it's easier to recreate this data. And then instead of creating a new plot, I'll show you how you can use an existing plot. All you do is select an existing plot, change the data by hitting the select data. You right click on the chart and you do the select data, and then highlight the data you want to plot. It's very simple. That way you just carry over, you'll get this range, this pop-up, and all you have to do is highlight the range you want. It'll automatically change the data range, or you can type it in to that box above, and you can have a new plot based on the new data. So we're just going to copy the existing plot over. We're going to change the data range here. So that's what's happening. You're not really seeing it, but that's why I'm highlighting this area. It's this is the select data option. And now that I've changed the data, I just format a little bit. Okay. That looks good. Let's look at the final product. All right, here it is. So the question is, what can we say? There are a lot of things we could say. One thing that's obvious is that sine theta is less than theta. That's actually not a big thing to say. The other thing is a pretty good approximation between sine theta and theta. But exercise 3, tabulate and plot tan theta over the same range of theta. Okay. Similar way of calculating the angle, and all we do is calculate tangent using the Excel's tangent function. Bring that down, plot it. Remember, we're going to copy a plot. Yeah, that plot, that's a good plot. Let's just change the data range. Simple. That's all we had to do. All the work has already been done. Isn't that nifty? So what can we say about this new plot? Okay. So, looking at the plot, yeah, it's obvious that tangent is above the above theta instead of below. That's one observation. Another observation, you might have seen, it's not quite as good an approximation as the sine one. It's a good approximation, really near zero, but not over a big range. So now we'll get to a tricky one. We're going to do arc sine over the range from 0 to sine of 60, because it's arc sine, right? And what can we say about arc sine and sine and x? Okay, here what we'll do is we'll just switch x for y. We'll copy the data over, but x will be sine of theta and y will be theta. And we'll bring over the chart and we'll change the data range, and that's the wrong plot. Something went terribly wrong here. That should be x equals x. That's not a line. Something's wrong. And the thing that's wrong here is Excel's charts. This chart doesn't work with this kind of data. It's very confusing. It just doesn't work with anything other than evenly spaced data. It's a quirk of Excel that you have to know. But there's a trick around it, and that's what I'm going to show you right now. Change to scatter plot, which we used before in plotting the triangles. Scatter plot allows you to plot, well, obviously it's going to create a lot of dots, but you can reformat the dots to have a solid line. So you switch, you format the data series, and where it said no line, you change it to solid line. And then you hit the marker options, and you change it from automatic to none. And you do that with each of the two data series, and you're going to be able to get a good looking chart. So let's delete this chart. Let's highlight this area, but we'll use the scatter plot. So we do insert, chart, scatter plot. And then, like I said, we have to format this data. So we'll right click on that and we'll format data. We'll hit the paint bucket. We'll say, okay, we want a solid line. And then for marker options, we want none. Again, we want a solid line. We'll change the color because the color is often not the one you want. And then get rid of the marker. And then do some more formatting. Okay. That's looking like a good chart. So this is the final product. What can we say about the chart? Two things pretty obvious. One is that this, again, like tangent, it's above the x-axis, the line y equals x. But here, I would say the range where it's a good approximation, exactly the same range as for sine theta equals theta, or approximately equal theta. They are pretty much parallel plots. Okay, tabulate and plot 1 minus cosine theta over a range. And this range is, pay attention, this is a smaller range. This is 0 over pi over 180. That's only 1 degree we're going to plot. So we're looking very close to 0. So for this, for the increment, we're going to choose pi over 60 times 180. The reason why is we want to look specifically very close to 0 to kind of get an idea of what 1 minus cosine is doing. And this is what cosine, 1 minus cosine looks like. Let's format this a little bit better. Okay, just adding some chart elements here. Axes, titles. We don't need a legend. Okay, here's the final plot. So what can we say? That's a parabola. I can tell. That is exactly a parabola. The way I can tell is that the largest value is about 15 on this, and the midpoint a little bit less than 4. That's the midpoints should be 1/4 if it's a parabola. So I divided by theta squared to see if it's approaching a constant. If it's a parabola, it would be, and yeah, I can see it's a constant. It's 0.5. It's very close to 0.5. So I'm coming up with a hypothesis. The hypothesis is that 1 minus cosine over theta squared is approaching 1/2. This is purely based on the data. This is not based on theory. But if we can prove it, it will be based on theory, right? Let's prove it. What can we use to prove such a claim? Well, we know something about trigonometric functions and theta. We have the limit sine theta over theta. That might be useful. Maybe we could square it. and use that, combine that with the above limit. So, okay, I can see something here. Sine squared compared with 1 minus cosine. Sine squared is 1 minus cosine squared, right? And that factors. 1 minus cosine squared is 1 minus cosine, and 1 plus cosine. Okay, now it all falls through nicely. The middle term is approaching 1/2. That's easy to see. The two terms on the either end, those limits are clearly 1. So the whole limit is 1/2. Okay, we proved something here. And we proved it based on a hypothesis that we got from graphing. And we get a bonus right now, a corollary. 1 minus cosine theta is equal to sine squared theta over 1 plus cosine theta. This is, in fact, the best way to compute 1 minus cosine theta. You should not use the direct values. You should use formula 4. Note it's easy to prove things once you know that they are true. Graphing and analysis helps reveal these truths. Exercise 6. This will be the last one. We're just going to plot cosine theta in this approximation 1 minus 1/2 theta squared over the range from 0 to 60 degrees, just to see what it looks like. Okay, that's easy enough to do. For the nth time, we're going to calculate theta, cosine of theta, and then this approximation, we're just going to plug in the formula, 0.5, 1 minus 0.5 times theta squared. We're going to bring that down and plot it, and I could have copied over a plot and changed the plot area, but I guess I'm being lazy. I'm just going to do it all over again. Just format the axes. I got to change the spacing a little bit. Okay, this is a final plot. And what can we say about this plot? I think there are two things that we can say pretty quickly. One is, of course, cosine theta is larger than the approximation. But the other one, I think, jumps out at you. This is a really good approximation. Really good. Over a big range. Yeah. So, again, this is a nice discovery that we made through graphing. Okay, time to close the spreadsheet. Thank you.